Okay, hello everyone. So this can be the last video. Just want to give a general overview of how to interpret an OLS model. So we'll give an example here using using a regression model that tries to predict crime. So we will have a bunch of libraries here that we're going to upload as our first step, and have a crime data set on my GitHub. So we will read this in as crime data. We'll rename the column names. So we have crime per million, and I think this is going to be at the city level. So the crimes per million across different cities in the U.S. Young males, the share of young males in the city, whether or not the city is located in the South or not, average education, male to female ratio, total population, non-white population, unemployment of youth, unemployment of adult, median assets, and number of low salary workers. We'll do just some basic data manipulation. Don't have to worry too much about that. But we'll run the basic regression where we have our dependent variables, the amount of crime in a city, regressed onto a bunch of variables. You can take a look at the output if you want. Now we'll look at it a little bit later. But in general, the main results are that the crime rates are positively associated with wealth inequality, adult unemployment rates, education, and the rates of young male in the population, and some other kinds of interpretation. Now, what's important is that we do some model diagnostics and make sure that we're not violating any of the major OLS assumptions, particularly with respect to assumption 4 that I talked about in the previous video, which is that the conditional mean residual is going to be unrelated to our explanatory variables. And the way we check that is looking at the plot of residual error terms plotted against the fitted values for our y. And we can look at this looking at the plot of our OLS model crime.lm and tell it to return the first two different kind of diagnostics tests. So the first diagnostics test is plotting residuals against the fitted values, and we can see a little bit of nonlinearity in our plot, which would be a clear violation of our major assumption, where we assume that the residuals is not going to be related to or nonlinear related to the outcome predicted values for the outcome variable. If we look at the normal distribution of the residuals, we see that they do look to be relatively normal distribution, which is a good thing. But in order to get rid of this nonlinearity, there's a few things we can do. We can take logarithms of our variables, which tends to create more normal distribution of our variables and also of the residuals. We could also check for outliers in the data, like this guy here looks like maybe an outlier. We could remove some of the outliers. We can also remove some of the variables in our model. So essentially the practice here, the art, why they call data science an art, is there's a lot of different ways that we can tweak our model so that the assumptions of OLS are not violated, although those come at a cost. Maybe we remove a key explanatory variable and now we have a linear relationship, but we've just lost an important predictor, and we know it's an important predictor, and that could bias our results as a result of omitted variable bias. So there's oftentimes no absolutely correct solution. It's really like testing and retesting till you get a model that makes the most sense to you. One of the other assumptions is we don't want high multicollinearity. So if we do just a scatter correlation plot among all our variables in scatter plot form, we can see most of the variables look pretty good, except the expenditures per capita in 1959 are almost identical to 1960. So we see very strong high correlation between these two variables. And we could just, to see whether that's an issue or not, we can rerun another model called this crime.lm2, and we can remove the expenditure per capita for 1959, only keep in 1960, rerun the same model, and we can see if there's any difference in the results. So using Stargazer gives us a very beautiful table where the titles we're looking at the effects of public expenditures on crime. For instance, so if we have our public expenditure 1959, 1960 in Model 1, we can see there's a negative and a positive coefficient. Both are statistically insignificant, but we know these variables are very high collinear, multicollinear issue. So we can remove this variable from Model 2, and now we see that the effect, excuse me, the effect of our expenditure per capita in 1960 is positive and statistically significant, which is what we would expect. And we can also see a slightly higher F statistic, showing that our overall model fit is better when we remove that expenditure per capita. And I've also removed unemployment youth here. That must have been some multicollinear issues as well. Anyway, so you can play around. You can see you can play around with a lot of the different types of regression, including variables, excluding variables, taking logarithms of variables, different ways to run your model. And the important things to remember when interpreting the results is what these results are showing is partial correlations between our explanatory variable and outcome variable. They're, in other words, associations of the relationship strength between, for instance, expenditures per capita 1960 on crimes in cities, holding constant all of these other controls. But again, we don't know, we can't say that this coefficient is causing. So if we increase expenditures 1960, that this will automatically reduce crime. We just know that there is some positive association. Of course, your main issue is in areas that have initially very high crime levels, you're going to have more spending. So you might have reverse causation is a problem, and there could be other variables that we're not controlling for in this model that could give rise to omitted variable bias. So there's a couple of things you need to be careful about, not interpreting the model as being a causal model, just showing partial correlations. And the second thing is distinguishing between practical significance and statistical significance. If we have a very low p-value that shows the coefficient is statistically significant from 0. But you also look at the size of the coefficients, right? So for instance, the size of this coefficient 1.138 seems pretty high, and we can interpret what this means in terms of its effect. 1 unit increase will result in 1 unit decrease in crime. But if we look at some other variables here, so for instance, 0.003, this is not only not statistically significantly different from 0, as we can see from the very high standard error, but is also very close in size, in magnitude and size to 0. So even if this was statistically significant, we would say that the economic effect of the ratio male to female in the city really has no strong economic effect on association with crime. So there's a couple of things to notice: the statistical significance, which indicated by the asterisks here, and then also the size of the coefficient itself gives it the, we can interpret it both in terms of statistical significance and economic significance. Okay, so this is the last video for OLS. So it gives you some examples of how we can create pretty models and also how to interpret those models as well. Okay, so the next part will be on to the lab, which will have one part will be looking at this regression modeling functions in R, and then the second part will be looking at what we've done in the previous couple of labs with clustering, and this time we'll be adding some dynamics to look at transition in clusters over time. So take a look at the lab, make sure you get that done.